For the second part of 6364 on Taylor series and Maclaurin series, we're going to look at a few Taylor series here. So the Taylor series that I'm looking at for question number 4 says, I want to find the Taylor series for f of x is equal to 1 minus x raised to the negative 3 power at x equals 2. This is what makes it a Taylor series. At a equals 2. That's what makes it a Taylor series, because I'm changing my center for my series. So if I'm changing the center for my series, how is that going to affect the series? We've done this series before, but we'll do it again. We start with our first term, which is our f of x term. And f of x is equal to 1 minus x raised to the negative 3 power. Then we find our derivative. And if you remember, we did these derivatives before. This is negative 3, 1 minus x to the negative 4 power times negative 1, which we wrote as negative 3, 1 minus x to the negative 4 power. And the second derivative was 3 times 4, 1 minus x to the negative 5 power times negative 1, which gave me 3 times 4 times 1 minus x to the negative 5 power. And the third derivative, I won't do them anymore. I'll just remind you that that was 3 times 4 times 5 times 1 minus x to the negative 5th power. And the fourth derivative was 3 times 4 times 5 times 6 times 1 minus x to the negative 6th power. Now that we have our Taylor series derivatives, we need to evaluate those derivatives at a equals 2 this time. So we'll start with evaluating f of 2. And if I look at f of 2 and I plug in 2 into my original function, I'm going to get negative 1. If I plug 2 into my derivative function, I'm going to get 3. If I plug 2 into my second derivative function, I'm going to get negative 3 times 4. So check your negative signs on these. They're a little different here. If I plug 2 into the third derivative, I get 3 times 4 times 5. And into the fourth derivative, plugging in 2, I get negative 3 times 4 times 5 times 6. So let's look at what our f of x function would be here. Our f of x function, we're going to keep that first term, negative 1, and then remember, this is the series, the Taylor series, so it's going to be plus my coefficient of 3, and now it's centered at 2. So now what's different here is I have x minus 2 to the first power over 1 factorial. So then the next one is, there's a negative sign there, so that's negative, and we can write that as 12, or we could write that as 3 times 4, so maybe we can see what we did before, and we have x minus 2 squared over 2 factorial, and then we have positive 3 times 4 times 5, and that's going to be x minus 2, so that's cubed, and that's 3 factorial, and now I'm going to have a negative 3 times 4 times 5 times 6, and that's going to be x minus 2 to the negative 4th power, and that's going to be over 4 factorial. And of course, I continue that. So you notice what's different here, besides our values that we got being negative and positive, is it's centered at x minus 2. So we need to find the summation here, and finding the summation is literally like we did before. We kept that negative 1 out, so we'll keep that negative 1 out, and then we're going to add the summation. So remember, this is my n equals 1 term and 2 term and 3 term and 4 term, right? So we're going to have n equaling 1 to infinity, and we found all of these 3 and 3, 4 and 3, 4, 5 and 3, 4, 5, 6. We've already done this. This was n plus 1 times n plus 2. And then we divided that, we multiplied that by x minus 2. This time, before we multiplied by x to the n power. Now we have x minus 2 because this is a Taylor series centered around 2. We still divide by 2 because we had this all gave me that factorial that we had before. And the only other thing that we need to add here is how do I change signs? And I'm changing signs. The 0 one is negative. The even ones are negative. So this is going to be x minus 1 to the n plus 1 power. So there you go. We just did our first Taylor series. Let's look at another Taylor series here. This Taylor series says approximate the function of f of x for the cube root of x by a Taylor polynomial of degree 2 at a equals 8. So when they're asking for a Taylor polynomial, they don't want the series summation notation. That's not what they're asking for. They're asking for a polynomial of degree 2, so like x squared plus x plus some constant, right? Maybe some numbers out in front. And ours will probably look backwards, a constant, an x, and an x squared. So it looks to me like I'm going to need the first 3 terms. But we still want to develop our full on how do I find that series. So we start with f of x, and that is x to the 1/3 power. And we take the derivative of f of x, and the derivative of f of x is 1/3 x to the negative 2/3 power. And we take the second derivative, and that second derivative is, let's see, if I bring that negative 2/3 out in front, I get negative 2/9 x, and if I subtract 1 from the power, I end up with negative 5/3. And if I take the third derivative then, and I bring that power up in front, I end up with negative 5, let's see, let's multiply 5, negative 5 times 2, and I end up with 10/27 x, and I'm going to subtract 1 from that power, so I'm going to get negative 8/3. And that should be all that I need. So now the next step, just like we did before, is to find f of, and this time I'm doing f of 8. So I'm going to plug in 8, and I want the cube root of 8. Because that's what we're doing here. That's the cube root of 8, so that's 2. Then I'm going to plug in 8. And I plug in 8, so I have 1/3, just so you can see what's happening here. And I'm plugging in 8, so I have the cube root of 8 squared. So the cube root of 8 squared is 2. Oh, and it should be to the negative 2 power, right? So we'll go ahead and figure that out, and that's 1/12. And then I'm just doing the same thing. I'm plugging in 8. And I'm just going to tell you what I get here. That's negative 1/144. And I plug in 8, and I should say this is my first derivative and my second derivative and my third derivative. Let me make sure I have my notation right. And if I do that, I get 5/3,456. So now let's look if we can start to kind of write this series. So our Taylor series of degree 2 of x is equal to f of 8 plus f primed of 8 times x minus 8 over 1 factorial plus f primed of 2. And I only need the first 3 terms of 8 times x minus 8 squared divided by 2 factorial. So what did that do, right? Let's clean that up just a little bit. And f of 8 we know is 2, and f primed of 8 was 1/12 times x minus 8, and 1 factorial is just 1, so I didn't need that, plus f double primed of 8 is, oh, that's a negative 1/44, and that's going to be x minus 8 to the 8th power. I don't need to figure that out, and that's going to be times 2 factorial. So we'll clean it up one more time, and we'll get our Taylor series is equal to 2 plus 1/12 x minus 8 minus 1/288 x minus 8 squared. And I just found a second degree Taylor polynomial to help approximate the function x cubed. Now let's approximate the sine of 12 degrees. And we're going to approximate the sine of 12 degrees to 6 decimal places. So first thing I want to do is I want to take this and I want to convert it to radians. So if I have 12 degrees, that's 12 degrees times pi over 180, which is equal to pi over 15, which I don't know what the sine of pi over 15 is, but can I use Taylor series to approximate the sine of pi over 15? I'm going to go ahead and just write down the Taylor series here. I know that we never discovered it together, but hopefully if you think about what we did when we discovered the cosine series, you can think that you could discover the sine series also. And this series, by the way, is also in your notes. If you look underneath your Unit 5-6 tab, underneath the notes, you'll find a whole slew of Maclaurin and Taylor series. So this is underneath there, and this is the Maclaurin portion of it. So I'm just writing down the series as I saw the series before, thinking about what would happen if I would expand this thing. And I'm not going to expand it like I said. I think hopefully you can make a connection between this series and the cosine series. So there that is. That's the series for sine of x. So now let's look at, we want sine of pi over 15. So we're going to plug in pi over 15. And we're going to keep in mind, remember that we want 6 decimal places. So we're going to have pi over 15 minus any place I see the x, I'm going to plug in pi over 15. I'm just plugging that into the x cubed, and I'm plugging that in to the x to the 5th power. And I'm plugging that in to the x to the 7th power. And I'm plugging that in to the x to the 9th power. And these should be 15s. I don't know what happened to my ones there. And I'll plug it into the x to the 11th, but that doesn't make sense to subtract 1 because we don't want it to get any smaller normally at that point. And let's go ahead and figure out what these decimals are then. So the sine of pi over 15, obviously it's equal to more here, right? Is approximately equal to, and I'm going to figure out these decimals. This is 0.2094395. That's the first one. The second decimal is negative, because I got a negative sign there, 0.0015312. The next one that I found is plus 0.000003. Now, I got to be careful here because I want 6 decimal places, and that's the 6th decimal place. So I'm going to look at the next one and see if it's going to help me, and I would be subtracting, which doesn't make sense that it would help. And I have 8 zeros here and a 4. So I don't need that because that's not going to help me get to that decimal place. This should do it for me. So if we add all those up, we find out the sine of pi over 15 is approximately equal to 0.0279113. And we wanted 6 decimal places, so our answer would be 0.207911. Now, if you use your calculator and you find the sine of pi over 15, it's using some sort of algorithm like this, and it will tell you that it's equal to 0.0 or 0.2079116,908, and obviously that keeps going on and on. So we did a pretty darn good job of estimating. You'll see right there on that 7th decimal, we were a little off because they had 6 and we had 3. And that just comes because we stopped at the 6th decimal. That's all that we were worried about. I hope you enjoyed these videos and you enjoyed Calc 2 because this is the end of Calc 2. I certainly have enjoyed doing these videos for you. Please come back and watch them anytime you need to refresh.